Hello, I am Professor Shubhi Sarkar from Department of Geological Sciences, Jadavpur University. Today, I will talk on primary sedimentary structure and palaeocurrent analysis. Both these two aspects are very vital to understand the sedimentary milieu of a sedimentary rocks. So, I should start with primary sedimentary structure and then I will switch on to palaeocurrent analysis in the second part of my lecture. So, primary sedimentary structure are formed during or immediately after sedimentation, but must have been formed prior to lithification. The structure in sediment piles are diverse in origin and form in different timings with respect to sedimentation. As this structure formed during sedimentation, they bear the signature of dynamic processes involved in sedimentation. Based on flow dynamics, this structure can be subdivided into depositional and erosional. Besides, there are biogenic and soft sediment deformation structure which are also considered as primary sedimentary structure. Organically influenced structure record the organism substratum interaction history. Soft sediment deformation structure on the other hand encompasses all the deformation structure formed during or after deposition. These syn-sedimentary deformation structures include those formed during sedimentation, reflect the then substratum condition. Other formed close to but after sedimentation is called penicontemporaneous or metadepositional deformation structure. Usually the primary sedimentary structure do not have any depositional bias, although there are very few structure which are restricted to particular depositional environment, as for example desiccation cracks, rootlet marks and structure associated with evaporites are significant example in this respect. Primary structure bears signature of flow dynamic processes involved in sedimentation, which can be shared by different depositional environment. Bed is the most fundamental primary structure because it represents individual flow, and beds are the basic building blocks of sedimentary succession. On the other hand, lamina are the building blocks of beds which represent fluctuation within a flow. It is a sedimentation continuum delimited below and above by omission surfaces, either erosional or non-depositional in nature. Beds are generally tabular or lenticular in geometry and has lithologic, textural and structural unity that clearly distinguishes them from the layers above and below it. Bounding surface of a bed are known as bedding plane. They represent either erosion or non-deposition or abrupt change in depositional condition. Bedding planes can be of various types: planar, wavy or curved. Groups of similar beds or cross beds are called bed set or set. A simple bed set consists of two or more superimposed beds characterized by similar composition of texture and internal structure. A group of two or more set is called coset. Beds are produced under essentially constant physical, chemical and biological condition. Beds can be produced rapidly by a single flow which result in the formation of massive bed, while slow deposition leads to the formation of either graded or laminated beds. Laminated beds can be of two basic kinds: planar laminated and cross laminated. In case of planar laminated beds, internal lamina are essentially parallel to the bedding, while internal lamina of a cross laminated beds deposit at an angle to the bedding planes. Surface geometry of a bed in response to prevailing condition is the bedform. A bed form is produced as soon as the flow attains a force sufficient to entrain particles from the bed and start transporting sediments and form a set of structures. If buried and preserved, bed forms will form sedimentary structures. The variables influencing bed form are nature of the flow, either unidirectional or oscillatory, flow depth, flow strength, fluid viscosity, fluid density, grain size, sediment density and acceleration due to gravity. To understand the dynamics of bed form, one should have some ideas regarding the flow regime concepts. Flow regime is the relation between the flow parameters, nature of sediments and the bed form and their internal structures. The flow regime concept is primarily applicable for products of channelized water flows with free upper surface. Relevant data are derived from studies in the field of fluid dynamics, hydraulic engineering, geomorphology and physical oceanography, where a direct observation between relevant factors is feasible. Some idea regarding the hydrodynamic principle of the flow is to be needed to understand the nature of bed form configuration. There are mainly two types of flow in nature, namely laminar flow and turbulent flow. In laminar flow, each of the point in the liquid moves along a straight line parallel to the bed, but in case of turbulent flow, each point follows an irregular path, so the eddies can form. The nature of the flow, whether it is laminar or turbulent, is measured by Reynolds number. It is a dimensionless number expressed by Re is less than 2000, the flow is a turbulent flow, while in case of laminar flow, Re should be less than 2000. For flows in open channels, the other most important coefficient of fluid dynamics is Froude number. Froude number can be considered as the ratio between inertial force acting on the fluid and the gravity force acting on the water surface. It can be represented by F is equal to V by G into H, where H is the depth of the channel, V is the mean velocity and G is the gravitational acceleration. A Froude number separates two distinct types of fluid flow in open channel. If Froude number is less than 1, that flow will come under lower flow regime, and if it is greater than 1, it will come under upper flow regime. Each type of flow represents a set of particular flow condition known as flow regime. So, student, please see the figure. You will see some plane bed which has formed in the lower flow regime. These bed forms are flat and almost featureless, internally planar laminated and generally present both in silt and fine sand. The sediment mainly transport as suspension load and rarely as bed load. You see in this figure, bed form produced by unidirectional flow. Here you will see an array of bed form can be generated by the unidirectional flow depending upon velocity, grain size and depth of flow. Ripples are the most common amongst them. As the flow velocity increases, the ripple enlarge until they form sand waves and finally dunes. At higher velocity, the plane beds are replaced by antidune, evenly produce shoot and pools. As I mentioned earlier, ripples are very common primary structure. There are two types of ripples, for example, current ripple and wave ripples. Current ripples are the commonest bed form encountered within the lower flow regime unidirectional flow condition. Student, now you see the photograph, they are dominantly formed by the bed load movement. they are asymmetric with a steeper downstream facing lee side and a gentle upstream facing stoss side. Mostly they erode the upstream side, that is stoss side, and accrete on the downstream side, that is the lee side. Avalanching along the lee side take place after the sediment accumulation on the crest reaches to the angle of repose. Dunes, on the other hand, are larger than ripples, and they are generally asymmetric bed forms, dynamically different from that of the ripples, commonly forming in the sand coarser than 0.15 millimeter. They are larger bed forms with wavelength more than 1 meter or more and heights of several tens of centimeter. The shape of the dunes is described as 2D if the crests are straight and 3D if the crests are curved. Sand waves, on the other hand, are low, appearing to be transitional phase between the two bed forms, namely ripples and dunes. Sand waves are low and straight to sinuous crested bed forms with well defined lee surface and stoss sides. Upper florism plain beds, on the other hand, also contain plain beds. These plain beds are flat beds with intense sediment transport, flow parallel mounds known as current lineation or parting lineations, characterized by flow parallel ridges and intervening furrows arranged in a echelon fashion along the length of the flow. Now you see the diagram, minute flow parallel eddies moving along the helical coiled path developed on the sediment flow interface and coarse grain settle between the uprising eddies, forming minute parallel ridges produce parting lineations. Such ridges remain parallel to the flow directions. Now antidunes is another type of bed form which form in the higher florism. They form when the flow condition is very rapid, and antidunes are gently sloping, long crested undulatory bed forms with low relief. Internally low angle cross beds directed towards upstream. Now see the diagram, these are the bed form stability diagram. The three major controlling factors for generation of different types of bed forms are mean velocity or stream power, grain size of the sediment and depth of the flow. The condition under which a given bed form will develop depend on the combination of fluid and sediment properties. The conditions are flow velocity, flow depth, water temperature, grain size, grain density. Besides, sediment sorting coefficient and particle shape have also considered being secondary importance. Now see the figure, bed form produced by multidirectional flow. You see here multidirectional flow can be of oscillatory or bidirectional in origin. On the other hand, oscillatory flows typically produce wave ripples. Wave ripples are generally symmetrical or slightly asymmetrical. Crests are generally straight to sinuous, sharp and bifurcated. The migration rate is less and their accretion always dominates. Oscillatory flows are often combined with current components. In shallower depths, wave path gets flattened and eventually breaks after touching the sediment water interface. The flattened wave pathways indicate combined flow condition that is oscillatory in motion is coupled with current component. In very shallow water, different wave sets can coexist and their interference produce a complex pattern of ripple set known as interference ripple. Now, you see the photograph here, some special type of bed form. Here you will see some hummocks and soil. These are undulating bed form which are thought to be formed by wave generated oscillatory flows or combined flows. The bed form shows dome shaped elevated areas separated by depression. The lower bounding surface is erosional and undulatory. Sediment drape over that surface to give an undulatory dome basin like appearance. Domal elevated areas are known as hummocks and depressed areas in between are called swells. So, now we should discuss about cross stratification. So, all the stratification deposited at an angle to the main depositional surface due to primary process are known as cross stratification, normally bounded between bounding surfaces. Cross stratification form primarily because of migration of bed forms, mainly dune, ripples, etc. Conventionally, if the individual inclined layers are thicker than 1 centimeter, the cross stratification may be referred as cross bedding. Thinner inclined layering is called cross lamination. It can also be formed by filling of scour and scour pits and channels by deposition on the point bars and meandering stream by the deposition on the inclined surfaces of beach and marine bars. So, cross stratification can be formed under many depositional environment. Now, you see the figures. Ripple or dune migration leads to formation of dipping forced lamina owing to avalanching or suspension settling in the zone of separation on the lee side of this bed form. If suspension load is negligible, avalanching of the bed form bed load sediment down the lee side of the ripple will produce steep and straight forced laminae having approximately the same angle to the angle of repose. Such internal cross strata is known as angular cross strata. If suspension load is considerably high, or if the height of the lee side of the ripple is small compared to the flow depth, suspended sediment will pile up at the base of the lee slope rapidly enough to keep pace with the growth of the avalanche deposits, causing the lower part of the forced laminae to curve outward and approach to the bottom set laminae asymptotically. If the suspension load is very high, then the fall along the forced over the lee and part of the crest area, hindering erosion of the crest and produce sigmoidal type of cross strata, where both the lower as well as the higher part of the forced lamina approach the bottom and top set laminae asymptotically. They are common in tidally influenced environment. Deposition over the point bars of meandering rivers typically produce large scale sigmoidal cross strata known as epsilon cross strata. Now, see this figure, cross strata are divided into two principal types on the basis of formative depositional mechanism, tabular cross strata and trap cross strata. Tabular cross strata form due to migration of 2D straight crested ripples and dunes. On the other hand, trap cross strata is formed by migration of 3D ripples and dunes formed under comparatively higher flow condition. Now, see this figure how a ripple cross lamination form. Ripple cross lamination, that is climbing ripple cross lamination forms when net deposition takes place very rapidly due to migration of current ripples. During aggradation ripple climb one on another in such a manner that the crest of vertically succeeding lamina are out of phase and appear to be avalanching upslope. Three kinds of ripple cross lamination are observed depending upon the relationship between Stoss angle and angle of climb. If the climb is subcritical, then the angle of climb will be less than the angle Stoss angle. If the angle of climb is equal to Stoss angle, then it will be critical climb. If the angle of climb is greater than the Stoss angle, then it will be supercritical climb. Now, you see the erosional structure. Erosional structure created by the flow immediately before it allows sedimentation are often preserved at the sole of the beds. Erosional groups created by the flow vortices include flutes and gutters. Particle movement in the flow give rise to diverse kind of structure like groove, prod, bounce mark, skip marks, as well chevron marks. All these structures are very useful indicators of palaeotop as well as the sense of palaeocurrent direction. Erosional structure can be grouped into two classes which are formed by tools or other group formed by currents. When it is formed by currents, they are generally shooting currents and they produced small channels and scours on the substrate. They are example are flute cast, longitudinal scour and gutter cast. On the other hand, when tools are involved for the scouring, they generally some object are on the participate in the flow, and their example are groove, chevron, prod marks, etc. So, now we should start with another type of sedimentary structure which are known as biogenic sedimentary structure, which are formed due to interaction of sediment with living organisms. Organisms may be animals which can move, or they may be bacteria, algal colonies which trap and bind sediments to produce layered structures. Biogenic structures can be subdivided into two categories: trace fossils or ichnofossil and biostratification. Now, look at the picture. Trace fossils are not true bodily preserved fossil, but are simply biogenic structure. They originated through the sediment, through the locomotion, feeding, burrowing and resting activities of organism. On the other hand, biostratification are the products of sediment trapping and binding by bacterial and algal colonies which form the convex up layered structure known as stromatolites. These stromatolites are very common example of biostratification structure and present abundantly within the Proterozoic carbonate deposits. Recently, there are another group of structure has been reported world over. Those are known as microbial induced sedimentary structure or microbially related sedimentary structure. Those have been reported from siliciclastic sedimentary rock all over the world. The other type of sedimentary structure are soft sediment deformation structure, include structure formed by the deformation during deposition, as well as the structure which are formed immediate after deposition but prior to lithification. The deformation structure produced during deposition are known as syn-sedimentary deformation structure, and the structure which are formed immediately after deposition but prior lithification are known as penicontemporaneous or metadepositional deformation structure. Deformation producing this structure can be triggered by some external cause like seismic jerk or internal cause like overpressuring due to quick dumping. If triggered by external cause, the structure usually found to be restricted within a single sedimentation unit with lateral extension. Now, you see the figure, genetically this subsediment deformation structure are of following varieties. Gravitational instability structure produced because of gravitational instability. These are formed due to density driven subsediment deformation, generally restricted within a particular sedimentation unit, overlying and underlying by undeformed undisturbed sediment. Example of this sort of structure are convolute, load structure, ball and pillow structure, flame structure. The structure which are formed by downslope movement are slump growth faults. Because of fluid flow, some structure also produced as for example overturned crossbedding. Fluidization and liquefaction are the two important processes for subsediment deformation. These two processes actually facilitated all kinds of subsediment deformation structure to form by reducing the cohesion amongst the grains. So, now we shift to another chapter which are related to this primary structure and how we can utilize this primary structure for interpreting depositional environment. Truly speaking, just direct correlation of primary structure with the depositional environment is often ends with dissatisfaction. An attempt can be made to evaluate the potential primary sedimentary structure as environmental indicators in broad terms. Frequent occurrence of wave structure in a sedimentary body most certainly indicate deposition in a wave agitated environment. It may be shallow marine or lake. In a lake, tide without synchronization with open ocean tide has amplitude only up to a few centimeters. No tidal bedform is thus expected in lacustrine deposits. However, the most convincing proof of tidal action is derived from the demonstration of laminar thickness variation in periodicities corresponding to those of tides. Now, you see the structure, the figures, there are some figure, one is herringbone cross strata, sigmoids, thick thin lamina alternations, mud drapes, double mud drapes layer, cyclic variation in forced geometry. These features are very much helpful for tidal influence sedimentary environment. As grain flow process operate more frequently, inverse graded dunes cross strata are far more common in aeolian deposits. Common occurrence of regular alternations between grain flow and grain fall strata, translaton strata or ripple climbing, adhesion ripple lamina can be very good criteria for identifying aeolian deposit. Wind ripple characteristically have very low amplitude but wide wavelength. Another part of my lecture, that is palaeocurrent analysis. Now, most of the cross bedding except some accretionary form are reliable palaeocurrent indicators. The palaeocurrent analysis is an important tool for basin analysis study. It gives the direction of the flow which was responsible for generation of the structure. The true deep of the foreset plane reconstructed from two orthogonal sections is used for determining the palaeocurrent. In case of trough cross stratification, the bedding plane expression or the traces of the trough on the bedding planes are very useful for measuring palaeocurrent direction. The acute bisectors of the two tangents drawn on the two arms of the traces of the troughs give the reliable palaeocurrent direction. The lee of the ripple slope also a good indicator of current direction. Besides, some erosional structure, for example fluid cast, are also useful indicator of paleo flow direction. Consistency of a current depends upon the steadiness of the flow. Long term consistency of palaeocurrent indicates stability of the current system. In tectonically unstable setting, long term stability of palaeocurrent is not expected. Palaeocurrent may be unidirectional, unimodal, bimodal, bipolar or polymodal. Unimodal palaeocurrent is expected in fluvial depositional environment. Bipolarity and bimodality are common in marine deposit. Tidal deposit generally show this pattern, though unimodal records are not uncommon from tidal deposit. Deposits of wave can also produce bipolar palaeocurrent. Aeolian palaeocurrent is generally polymodal in nature. As mentioned, fluvial palaeocurrent pattern is likely to be unimodal, but degree of consistency of the palaeocurrent also varies between meandering rivers, braided rivers and straight channels. The relation between palaeocurrent direction and deep of the depositional substrate is important for regional interpretation. Fluvial cross strata generally have a mean direction towards deep of the depositional substrate. However, Aeolian cross bedding does not have any relation to paleo slope. Shallow marine palaeocurrent also does not always maintain any particular relation with the paleo slope. It may be parallel to the slope, even across slope. In case of longshore current, the direction is parallel to the shore line. Shoal structure, particularly fluid cast, prod marks, also provide good information about palaeocurrent direction with sense. Some other shoal features such as gutters, group cast provide direction without sense. Similarly, parting lineation provides unidirection without sense. Fossil orientation may be helpful at places, but their relation with palaeocurrent is not always same. Pebble imbrication in conglomerate deposit may also be helpful for getting the palaeocurrent direction. Now, we should summarize the whole thing so far we have learned. So, we start with palaeocurrent we start with different types of sedimentary structure, and we have learned varieties of sedimentary structure, and these structures are present in different hydrodynamic different depositional environment, and this structure can be shared by different depositional environment as well. But so it is not very wise to interpret the depositional environment from a particular particular primary sedimentary structure, but if we consider different structure as a whole, we can identify a paleo environment as well. And also we have learned that the palaeocurrent is very helpful for basin evolution study, and from different primary structure we can identify the palaeocurrent direction, and that ultimate we can plot in a simple Rose diagram, and we can conclude about the then current direction which were responsible for formation of the primary structure. Thank you.